So the lecture notes have briefly talked about the four fundamental forces of the universe. The gravitational force, the strong nuclear force, the weak nuclear force, and the electromagnetic force. In this course, we're really not going to be talking about the strong or the weak nuclear forces. You'll see that more in astrophysics, radioactive decay, or nuclear physics. For this case, we're really going to just be focusing on gravitational force and electromagnetic force. And in those, the specific types of forces we're really going to be dealing with, gravitational force, which is essentially gravity attracting objects. We're mainly going to be looking at gravitational attraction of objects on Earth, but we will do a few examples of like planet to planet gravitational interactions, or even like our sun to our planet gravitational interaction. The reason actually Earth orbits the sun is because it's gravitationally attracted to the sun. The sun is massive. It pulls in 7 other planets in its orbit amongst an asteroid belt. 8 if you're still considering Pluto a planet, which some people do. That's okay. That's up to you if you want. But it gravitationally attracts a lot of things. Earth gravitationally attracts our moon. Saturn gravitationally attracts its own moons. Jupiter gravitationally attracts everything. But that's kind of the idea behind that. Gravitational attraction, for the case we're going to be looking at in specifics, Newton's equation for gravity, Fg. And this is equal to the gravitational constant, which I'll talk about in a second, the mass of one of the objects, the mass of the other object, divided by the radial distance between the two of them, squared. Now, this is what's called an inverse square law. And a fun little side note I think is worth mentioning is electromagnetic force. If I'm looking at just the force between electrons, we won't look at it much in this context, but we will for this case, is equal to Coulomb's constant, the charge of one particle, the charge of the other particle, divided by their radius squared. These are both what we would consider inverse square laws. And both are like, these are make up half of the fundamental forces of the universe. So there is something very distinct and unique about our universe that is governed by this inverse square law. And you can think of this, that's a fancy name for just saying it's not proportional. So if I move farther away from an object, I could kind of graph this in terms of the gravitational force of an object and the distance that object is away from it, and it's going to kind of decrease as an exponential decrease. Now that's not supposed to go up. I'm just really bad at drawing. A fun thing about this is it never quite goes to zero. So it's an asymptotical relationship. It doesn't actually cross zero because it can't, because the numerator is a constant positive numbers. It can just get smaller and smaller and smaller, which is why I don't really feel the sun's gravitational pull. I'm on Earth. I'm so close to Earth, which is why Earth is the strongest gravitational pull I can feel. I don't really feel the sun's gravitational pull on my body, right? Earth does on it because it's big relative to us, but we really feel Earth's gravitational pull. We're not going to be all of a sudden lifted off and thrown to the moon or thrown to Jupiter because our proximity, because of our distance. And the same thing is true for how electromagnetic forces are fundamentally governed. Again, we're not going to focus too much on the electromagnetic force equation just yet, but I do think it's important to note they follow that same mathematical principle, which is fun because, I mean, come on, math is cool. So that's the gravitational force equation we will be looking at for this case. And then, so that's really the only force of these 6 forces that I've kind of mentioned up here that is a gravitational force. The rest are technically electromagnetic forces, which is so fascinating to me. So the push force, for example, you might be thinking, how is this an electromagnetic force? But so let's just kind of try and draw a diagram. This is a hand. I'm not a drawer. I'm not a very good drawer. And then this is a block, okay? So this hand is going to push this block this way. I want you to think, why does this in terms be defined as an electromagnetic force? My hand is made up of atoms, elements, and particles. They have electrons and protons and neutrons. They're made up of substances. The block is also made up of elemental particles. It has atoms, electrons, neutrons. And some of those forces attract, some of those forces repel. So my hand pushes against the block, and technically I never actually touch the block. My electrons push against the electrons made up of the block. And they then repel each other as an electromagnetic force. I can apply a force to the block. For this course, we're never really going to call it an electromagnetic force in terms of the electromagnetic equation. We're going to call it an applied force. I'm pushing a force onto the block. And we can measure that force using a lot of various things. But essentially, that's going to be our governing of the push force. Pull force is the same case. I could tie a rope to this block. I could pull the rope. I could pull it this way. The rope is made up of particles. Those particles want to stay together. They want to not break apart. They're going to hook on together and pull the block with it. So that's kind of the idea between the pull force. A frictional force, again, an electromagnetic force, and I can think of, if I rub my hands together really quickly, I produce heat. You've probably heard people tell you that that's kinetic friction that you're making. Yes, kinetic. So there are two types of forces. What frictional forces we'll actually talk about are static and kinetic. So static and kinetic. Static is when it's stationary, when it's not moving. So static friction of an object to keep it from moving. And we'll explain that. If a block sits on the ground, it is experiencing, I mean, if the ground is completely horizontal, so we can kind of understand the free body diagram from the last video. Gravity is going to pull it down. Normal force of the floor or the ground or whatever it's sitting on is going to keep it up. Those should be equal and opposite. Now, if it's on a completely level plane, it's technically not moving. So static friction, we would say, is zero, because frictional forces, it's important to note, are only ever opposing motion or potentially opposing motion. So in the case of static friction force, it's technically an inequality. It's not an equation. So the inequality, the way we'd set it up is, I actually write it like this: capital F for force, little f for friction, s for static, is less than or equal to mu s n, where mu s, this is the frictional coefficient. This is a unitless quantity. This is very specific to what the material is made up of. And I'll pose it an example like this. Is it easier to push something across ice than to push it across carpet? Ice, right? Why is that? Because ice is made up of particles by its nature, by the things it's made up of and the type of atoms. It poses less resistance when I push something across it. Carpet, on the other hand, by the substance and material it's made up of, poses a lot more resistance. So mu, that's just the name for the Greek letter here, this is the frictional coefficient, is going to actually be two different numbers between when it's moving and when it's stationary. We'll talk about that later on. But it is specific to the material of the object itself, between two things. So, and the reason for static, the reason it's an inequality is because technically this particular block is not moving and there is no static friction on it. And I know that because it's an opposing motion. If it's completely horizontal, the block's just sitting on a surface that's completely horizontal, there's no motion for it to oppose. It's not going to move. I could, however, so I want you to think, if you have like a couch or a chair or a dresser, you could lean against it, or maybe you start pushing it, but it's really heavy, and you push on it, you apply force, and it doesn't go anywhere. You might ask yourself, well, why doesn't it go anywhere? I need to push harder. I need to apply more force. So there could be the case of, let's say this is now a dresser, and gravity is pulling it down, and a normal force is pulling it up. I apply a force to it, but it's heavy enough. The force I apply isn't great enough to counteract the force of the static friction for it, whatever is keeping it in stationary, right? I have to put more force on it then to get it to start to move. And so it can have a force that increases. And the reason why it's an inequality is it can only get so big up to a certain point that once I overcome that force, then it'll start to move. And that's why it's an inequality like that. For kinetic friction, this is basically kind of the same thing, but the object's always going to be moving. So this is, let's say, for example, of the dresser. Gravity is pulling it down. Pretend that's straight down. Sorry, really bad at drawing today. Normal force is holding it up. I'm applying a force, F, A. And let's say it's already moving. It could be moving in two cases. It could be moving as accelerating. That's kind of hard to do. If I'm pushing a dresser, generally speaking, if I'm like helping a friend move and we're sliding something across, probably going at a fairly consistent rate. Sometimes it's stop and go because the thing is heavy. It requires work to apply force and effort on that. We'll look at later. Once I get it moving, it can move at a constant rate. So it can still equal the kinetic friction, FFK. This doesn't mean it's not moving. It just means it's now moving at a constant rate. There has to be, to get from, so you'll notice, why are these both the same? But in one case, one isn't moving down here, and this one is moving, right? Why is one case, why are they different, even though they look almost the same? The subscript really matters here. FFK, FFS, that is what denotes, I know that the FFK is moving, it's kinetic. FFS is not moving, it's still static. And I can also do the math involved with it, which we'll look at later. But in this case, there has to be some acceleration between here and here initially to get it from static to kinetic. I have to introduce a momentary amount of acceleration, and put yourself back into the experience of moving the dresser. Once you get it going, it's an initial push. You almost, push it and it goes, and then you kind of slow down a bit. It's a little easier to push. This is why these two, and I actually didn't write the equation for this. Sorry, I know I'm jumping all over the place. The kinetic friction equation, this is an equation, is the almost exact same as the static. It's mu k n, which is, again, this is the normal force. These, and I should really rearrange, I'm writing these as F N. They mean the same thing. It's just a notational preference. But in this case, mu S does not equal mu K, even for the same set of objects. If it's the case of your friend, you're helping your friend push the dresser's probably made out of wood, pushing it across maybe carpet, something like that. The wood between the carpet, as it's stationary, has a different kinetic or static friction coefficient than when it's kinetic. And which is why once I start getting the dresser moving, it's almost a little easier to push than when it was not moving to get it moving, right? It required more effort to get it moving, but then once it's moving, it's almost a little easier. That is why. Just kind of a fun thing there. The next force we're going to look at is drag force. I'm going to write the equation, but we're not going to use it much in this course. I'm going to write it so you kind of get a general understanding of what it is just to begin with. But the equation is D for drag, is equal to 1/2 rho. This would be CD AV squared. And I'll just explain a little bit of these just so you at least have seen it once. Again, we're not going to go into too much detail on this. Rho is the density of the fluid of which I'm moving through. So in this case, oftentimes it's air. Air has a specific density based on just the substance of what it's in, which is why you actually have more drag when you're going through water. Water is more dense, right? So it's harder to push through water. You've seen endurance runners sometimes train in water, like treadmills. If you've ever heard of those, that's one of the reasons for that, is it increases more drag force. CD is called the drag coefficient. This is a dimensionless unit, has to do with basically the shape of an object. I mean, you can think of it as, why are parachutes built to be like really wide and far versus like you could have the same substance that the parachute's made out of, but maybe make it more narrow. It wouldn't be as effective, right? So this really has to do with the shape of the object. Like if I want to slow down my speed, I lay out flat on my stomach if I'm falling through the air, versus then like if I really want to go through, I can like tuck everything in and drop. This has to do with a little bit with that. Same as the cross-sectional area. Cross-sectional area, the wider area I spread out, those two kind of relate to each other. And then V is the velocity. This is the velocity of the fluid, not the object. So it's kind of a relativistic velocity. We won't go into too much detail on that. But that's kind of the idea behind this. Why this is an electromagnetic force is I am resisting the objects that I'm passing through in terms of a fluid, those have protons, electrons, and neutrons, which attract or repel my protons, electrons, and neutrons. So I'm resisting those as I move through them. So that's a little bit of the drag force. The spring force is the last one we'll talk about, and this has to do more with Hooke's law, which you've probably heard. The equation for which, so let's talk about a spring on the horizontal direction first. Okay. And I want you to think of a spring just as it's sitting out. It has stored in it, if it's sitting out in what's called an equilibrium position, it has no energy, no amount of force. I can compress a string, a string. I can compress a spring. If I let go, what's going to happen? It's going to uncompress. It's going to bounce. I can pull a string or stretch, or I keep saying string. I'm sorry. I can pull or stretch a spring, and if I let it go, it's going to compress. It's going to go back in. It's going to resist the motion that I've imposed on it. And the force that comes from this spring, I'm going to call it Fs from spring, is equal to spring coefficient, which is not unitless. This actually does have units of newtons per meter, times the horizontal displacement. So this is based off of how far away I stretch it from its equilibrium. So let's say that this is its equilibrium. I would denote as x naught. That's its happy place. Doesn't have energy, just wants to kind of stay there based on the substance of the spring. And the K, the spring constant, can be thought of a small, skinny spring is going to stretch easier than a really thick, big spring, right? So that is more to do with the substance material of the spring, just like the kinetic coefficients in a very similar manner. And then if I were to stretch it, this is its distance of stretch based on and the amount of force required to get it to that distance of stretch, or the amount of force it could store or push on an object is going to be related to that. So these are just a brief introduction into each of the forces. We're going to look at detailed examples of each of them because I know we just covered a lot, but just to kind of get a gist of some of the forces we're going to be working with, these are them.